Theoretical physics is a branch of physics that deals with the development of mathematical models and frameworks to explain and predict the behavior of the physical universe. Theoretical physicists use a variety of mathematical and conceptual tools to construct models and hypotheses that describe the fundamental laws of nature and the behavior of matter and energy at a wide range of scales, from the subatomic to the cosmological. Theoretical physicists often work in collaboration with experimental physicists, who perform experiments to test and validate their theories. Together, theoretical and experimental physicists work to advance our understanding of the fundamental laws of nature and to explore the mysteries of the universe. Without our understanding of the underlying mechanism of the nature, all kinds of today technology would be impossible. For examples, communication networking, global positioning system, GPS, high-performance computer and magnetic resonance imaging. The Institute for Fundamental Study, or IF in short, was officially inaugurated on March 14, 2011 by Naresuan University Council as a research center unit. From the first day to the present, IF members are working on the cutting-edge areas of research in theoretical physics to expand the boundaries of our understanding of the fundamental laws of nature, including cosmology, gravity, string theory, quantum information science and mathematical physics. We would like to emphasize that frontier research in theoretical physics is essential for advancing our understanding of the universe and developing new technologies that would benefit not only Thailand but the world society.
Okay. Good afternoon, everyone who actually in this room and watching online. And welcome to the Colloquium number 25, I think. Okay. And today we have a very special guest, Dr. Ratchaphat. Where is he now? Oh, he's come. Okay. Hi. So, well, actually, we're very familiar to each other because he is a postdoc at the IF, but he's working remotely at the KMITL. Is that correct? Right. Yeah. Oh, yeah. Sorry about this. Anyway, so today topic is about what? Let me see the topic, please. Cosmological model due to the non-extensive properties of the Rényi black holes. Okay, screen is yours. Okay.
Thank you very much. Thank you very much for inviting me for give a talk in this colloquium. Can you hear me, right?
Yes. Okay.
Oh, okay. Okay, so today I would like to talk about my research. In fact, this manuscript, I think my colleagues and I plan to submit within this month. So it is the very recent result that I will be present here. So the purpose of this talk, I would like to introduce the alternative description of the black hole thermodynamics. It's called the Rényi thermodynamics or Rényi entropy, and then apply it to the cosmological context. This is the outline of this talk. I separated mainly into two parts. The first one is about the black hole thermodynamics, and the second one is about cosmology. Okay, let us start with the entropy of the black hole. There is an interesting result from the Penrose work that he found in the process of extracting the energy from the rotating black hole. He found that the surface area of the black hole in that process is increasing. So he also suggests that this feature might be an important property of the black hole in general. After that, Hawking can prove it in any classical processes. The black hole never decreases its surface area at the event horizon. Based on such a property, we can remind it is similar to the second law of the thermodynamics. This actually motivates Bekenstein to construct the entropy of the black hole. During the process of construction, he found that there is no the classical quantity that can be put into the form of the entropy of the black hole purely, but it requires the effect of the quantum nature. So if we would like to study the thermodynamic property of the black hole, we actually need the quantum theory, but unfortunately there is no the best candidate for the quantum gravity right now. So it is maybe work on the semi-classical treatment. After that, Hawking tried to construct the, in fact, he determined the proportional coefficient between the entropy of the black hole and the surface area at the event horizon. He considered the quantum field on the curved space that can be thought of as the radiation that emits from the black hole. It is well known as the Hawking radiation. Based on this situation, he eventually determined the proportional constant like this. And we also obtained the temperature of the black hole. For the entropy, it is known as the Bekenstein-Hawking entropy, and the temperature is called the Hawking temperature. Here, for the temperature, it is actually proportional to the black hole quantities called the surface gravity. So for order, it's just like a Kb, just a Boltzmann constant, speed of light, c is speed of light, h bar is Planck constant, g is a Newtonian gravitation constant. Similar to the thermodynamics, we can construct the laws of the black hole mechanics, and there is the quantity, geometric quantity that link between black hole to the standard thermodynamics like this. Moreover, it is possible to construct the algebraic relation among the variable of the black hole, quantity of the black hole here. It is also known as the Smart formula. So let us consider the consequence of the entropy of the black hole. If we consider the composition law of the black hole, it is found that there exists the red term here, an extra term, which is make the composition law taken in the form of the non-additive form. It is just for the Schwarzschild black hole, but for other type of the black hole, it's also non-additive, but it should be taken in the more complicated form. It means like if we consider the standard Gibbs-Boltzmann statistic, it is contradict with such a composition rule here. So another the possible treatment is just to consider the generalized entropy, and let me type it. Let me write it as a general form with as a function of the ordinary Bekenstein-Hawking entropy or the Gibbs-Boltzmann entropy with the S-star parameter or the model parameter of the entropy that we have to consider. Based on the generalized entropy, we actually can define the temperature from the first law like this. However, the definition of the temperature give a consistency here. If we consider the algebraic relation among the black hole temperature with the generalized entropy, it is found that the algebraic relation is not valid for the generalized entropy, but it's still valid in the standard Gibbs-Boltzmann entropy or the Bekenstein-Hawking entropy. So we have to like extend the phase space, thermodynamic phase space, by treating the entropy parameter as another thermodynamic variable. To see this, we have to specify the type of the entropy first. Based on the composition rule that I have shown previously, it might be good to consider the entropy called the Soulis entropy. It is because this type of the entropy also has the additional term which make the entropy is now non-additive. But with this non-additive, it make that, how to say, it is very difficult to define the equilibrium state of the two subsystems that combine to each other. It is because it actually strongly depends on the composition rule of the entropy. In other words, we have the entropy that additive that is additive. It how to say? In order to define the temperature in the equilibrium state, it is also called the empirical temperature. The property, the extrinsic property of the energy and the entropy play the important role here. But the key idea is just make the non-additive entropy to the additive one. The solution is proposed by Below and One. They just map the non-additive entropy to be the additive one by using the green function here. It is called the formal logarithm map. After this map, we will get the entropy that the functional entropy that be additive. It is also seen that if we map the Soulis entropy, we get the entropy what we know is called the Rényi entropy here. So in this work, we focus on the Rényi entropy. by treating the area or the Bekenstein-Hawking entropy as a Soulis entropy. So the relation between the Rényi entropy and the standard Bekenstein-Hawking entropy related via the formal logarithm here, and the lambda here is called the non-extensive parameter. It is seen that if we take the limit lambda goes to 0, the standard Gibbs-Boltzmann or Bekenstein-Hawking entropy can be recovered from both Soulis entropy and Rényi entropy. So we have a specific form of the entropy that we are interested in. So the next step is to extend the thermodynamic phase space. The first step is just express the black hole quantity in terms of the entropy and its parameter. It is possible to rearrange the form of the mass of the black hole like equation 12 here. And it is found that this form is taken as a homogeneous function degree 1/2 of the variable Rényi entropy and the inverse of the non-extensive parameter. And then apply the Euler theorem to this homogeneous function. We eventually get the algebraic relation or Smart formula and the first law of the thermodynamics, where TR here is just the conjugate variable of the Rényi entropy. So we call the Rényi temperature, and psi here is just the conjugate quantity of conjugate variable of the non-extensive parameter. Okay, then if we take the limit in the small limit, and then just like take the series expansion to the psi, the conjugate variable, it is seen that the leading order is proportional to the three-dimensional volume. So it is possible to think the psi as a Rényi volume and non-extensive parameter as a pressure. Based on the first law, the form of the first law, the mass, the role of the mass in thermodynamic point of view is changed to the chemical enthalpy. Here. Now let us see the effect of the Rényi entropy to the black hole thermodynamics. If we consider the stability, technically called the local stability, which describes whether the black hole can exist by itself or not. If we consider in the normal situation, for example, if I have a glass of cold coffee and put it in the normal room with the normal temperature, the cold coffee try to absorb the heat from outside, from surrounding to it, and its temperature will get hotter and hotter, and the process is finished until the temperature of the cold coffee and the temperature of in the room temperature are equal. In oppositely, if I have a hot coffee, it's try to emit the heat to outside, and its temperature get colder and colder until its temperature equals to the room's temperature. If we consider the exotic case with the negative heat capacity. The behavior is opposite. Like, for example, if there is a system that colder than surrounding, it try to absorb the heat from outside, but its temperature is colder. It absorbs the heat from outside and it gets colder and colder. It just like it's never reached the temperature of the it's never reached the thermal equilibrium, which is the temperature of the system and the temperature of the surrounding are equal. And for the hotter case, it try to like emit the heat from outside, but its temperature itself get hotter. For the both case, it's like it's go away from the equilibrium state. So we can conclude that if we consider the system that called the local stable, we need the heat capacity being positive. For another type of the stability, if we have many systems that are locally stable, we would like to find out which one is preferred to exist in the nature. For this situation, if we consider the case that there is no system, now we can think as the black hole system. If there is no black hole, we can set the energy as a 0 because there is no system, there's nothing here. Compared to the black hole system, black hole phase with thermodynamic variable like pressure, volume, and temperature here. If the black hole has lower free energy, it should be preferred to form in nature compared to the phase without black hole, right? So we get the condition for global stability, like the free energy of the system must be less than 0 for our consideration, because we consider the phase without black hole and there is a black hole. By consider the black hole using the standard Gibbs-Boltzmann entropy, it is found that both heat capacity and free energy correspond to the unstable condition. So it cannot be formed in nature based on the Gibbs-Boltzmann entropy. But for the Rényi entropy, if we consider the local stability, we can determine the side of the heat capacity from the slope of the temperature. It is because the change in mass of with respect to the horizon radius is always positive. So we just care only the slope of the temperature. If we consider the effect of the non-extensivity, we can see that there exists the positive term due to the existence of the non-extensivity, or you can see in the plot here. For the red dash curve and the blue dot curve, is a non-zero non-intensive effect. So for large enough black hole, it can be locally stable. For globally stability, again, the contribution due to the existence of the non-intensivity can make the free energy be negative. As a result, we can plot the phase structure like this. The red curve is for the Rényi, the black hole described by the Rényi, and the backdash curve is the black hole described by standard Gibbs-Boltzmann entropy. Here, you can see that there is a phase transition, which is well known as the Hawking phase transition for the black hole described by the Rényi entropy, that transform the non-black hole phase to the black hole phase, actually stable black hole phase. This feature is similar to the result of considering the black hole in the anti-de Sitter space. So it is show like it is the key remark. The effect of the Rényi entropy is similar to the effect of the effect of the negative cosmological constant in terms of the black hole thermodynamics. Yeah, let us move to the cosmology. In this work, we focus only on the late time evolution of the universe. By study the dynamics of the universe based on GR, we start with an assumption that the universe is obey the spatially translation or homogeneity and spatial rotation or isotropy. For the curvature sector, the metric is known as the Friedman-Lemaitre-Robertson-Walker metric, and the parameter A here is called the scale factor that can be described the dynamics of the universe. The capital K here is just the spatial curvature. In this consideration, I take the spatial curvature as 0 corresponding to the spatially flat universe that strongly agree with the observation. For the matter sector, consider the perfect fluid. It is the simplest form of the fluid that obey such a symmetry. There are two quantities which are low, the energy density, and P pressure here, that can be described such a fluid. By plugging this into the Einstein field equation, and also we have to use the relation between the energy density and the pressure is called the equation of state. So to describe the behavior of the fluid, we just know only the parameter W, the equation of state parameter. We also know its evolution. So as a result of the Einstein field equation, we can write it in terms of the acceleration equation like this. And you can see that the universe will expand with acceleration when W is less than minus 1/3. Minus 1/3. And it's less than minus 1/3. The universe will expand with the acceleration, but based on the observation, it should be around -1. According to such a condition, there is no known matter. We have known only non-relativistic matter corresponding to the W equal 0 and the radiation W equal to equal to 1/3. So we have to introduce an exotic species of the matter called the dark energy in the universe to describe it. In this work, we actually focus on a model of the dark energy called the holographic dark energy. Okay, it's not only one of the treatment based on GR. Another treatment is called modified gravity that modify the curvature sector of the iodide field equation. Okay. So let's go to the definition of the holographic dark energy. If we consider the box of the volume L cube here, the entropy can be expressed as the volume scaling entropy for the normal system that described by quantum field theory, some quantum field theory, which has the UV high energy cutoff LU lambda UV here. Bekenstein found that the entropy of the normal system cannot exceed the entropy of the black hole. You can imagine like the ordinary matter can collapse to be a black hole, but the black hole cannot like reverse the process to become the ordinary matter. So a condition known as the Bekenstein bound. Due to the different scaling behavior of the entropy, for the ordinary matter, it's a volume scaling, but for the black hole, it's area scaling. They exist the sufficiently large scale that can, in which the quantum field theory breaks down. There is an argument by Cohen and his colleagues that propose that the ordinary matter, the system with ordinary matter described by some quantum field theory, never reached the Bekenstein bound, but it will face the energy bound before. And here it is the expression of the energy bound here. It is like the energy of the matter cannot exceed the energy of the black hole equivalently to the mass of the black hole. Cohen also claimed that in this regime, the quantum field theory is still valid. There is an attempt to define the situation that the ordinary matter has the maximum energy in which it doesn't form as a black hole as a energy of some vacuum or the dark energy. It is known as the holographic dark energy. So you can see that next is the high energy cutoff and the low energy cutoff here. So it also known as it also thought of as the holographic dark energy can be constructed from the high energy and low energy relationship or UVIR relationship here. And the parameter B is just the proportional constant. It is just the parameter of the model. By putting the length scale, we have to specify which length scale that describe a system. For example, if we consider the dynamics of the universe, we have to select the characteristic length scale as some cosmological length scale. For the first simple choice is the Hubble radius. Just put as a Hubble radius, and then plug it into the Friedmann equation. It is found that the Friedmann equation can be rearranged in this form, equation 13. It is actually just rescale the density, the energy density. So the evolution of the universe is exactly the same as the universe fulfilled with the ordinary matter. So this kind of this choice cannot drive the accelerated expansion. Another atom is called the particle horizon. Here it is the definition of this kind of the horizon. By seeing in detail, it is better to see in the conservation equation of the dark energy. With this conservation equation, we can determine the value of the equation of state parameter of the dark energy here. As a result, is also greater than minus 1/3. So again, this cannot drive the accelerated expansion. The last choice of this example is called the future particle horizon. It's actually the same form of the particle horizon as I showed previously, but it changed the limits of integration. In the particle horizon, we integrate from the past to the present, but in this type of the particle horizon, this type of the horizon, we integrate from the present to the future. It is found that the equation of state parameter for the dark energy is agree with the observation. It can drive the accelerated expansion, and they also have the correct rate of expansion. But this type of the particle horizon has a problem, serious problem. It is because you can see in the definition, we need to know the information in the future in order to explain the phenomena in the present time. But it doesn't make sense because we don't know what happens in the future, but we know what's happening now, right? So the situation leads to the problem of causality. There are other length scale that construct for the holographic dark energy, but we don't want to discuss about them. To see another approach to define the holographic dark energy, as I defined previously, it is obviously it is obviously that the energy density can be constructed from the quantity of the black hole, right? And it is strongly depend on, it can be thought of as it should be like a play with the property of the black hole. So if we consider the energy density from the change in mass like this, we can apply the first law of the thermodynamics to the form of the energy density. As a result, we get exactly the same result as defined from the UVAR relationship. And then go to the main of my work. I would like to modify the form of the energy density by using the author description of black hole thermodynamics. They also has another solution, which is the consider the author solution of the black hole. It is one of my previous work. And for this work, we just consider the same black hole solution, but different thermodynamic description. And in order to investigate the cosmological model, we don't want to deal with the causality problem. So I will use only the Hubble horizon as the characteristic length scale. So this is the definition of the energy density for the holographic density. And I consider the changing in mass under the isobaric process is actually motivated from the stability of the black hole. I mean, in the global and local stability that we have mentioned earlier. It is the form of the energy density here. In this, I redefine the non-intensity parameter in terms of length scale, L lambda here. And L here is just L subscript IR, but for convenience, just use only L here. It is useful to consider the asymptotic behavior. If we consider the very small L compared to L lambda, it is found that the form of energy density can be expanded like this, and the leading term is exactly the same as the original model. So it is just a scaling solution. The dynamics of the universe will evolve similar. The dynamics of this energy density will evolve similar to the dynamics of the dominant species in the universe. Oppositely, if we consider the large length scale limit, it is seen that the dominant term is almost a constant. You can see they contain the non-constant term, but it takes by the logarithm function. The magnitude of changing is separate pretty much, so it can be treated as the constant. If the energy density is constant, it's similar to the standard LambdaCDM model. I'm sorry for redefine the parameter many times, but for convenience in analyzing in the cosmological context, it is should be redefined the length scale compared to the Hubble parameter at the present. It's quite convenient in analysis. It is seen that if we define, it is called the density parameter here. There are two parameters, which are b square and L lambda for the model parameter of the Rényi holographic dark energy. It's just a constant that we have to evaluate. But for LH or the Hubble radius, dimensionless Hubble radius. It's just the dynamic variable that we have to evaluate by solving the Friedman equation. You can see that the model parameter L lambda and B square is actually dependent. If we consider the select, vary the parameter B square, we can see that in the late curves, the density parameter in some limit. Actually, this limit is the present time limit. The Hubble parameter equal to the Hubble parameter at the present time. So it should be not higher than 1. It is actually come from the definition of the density parameter. It should be higher as 1 as unity. So for the red line is, we cannot take the parameter, the B square parameter too high. But for if it's low enough, we can evaluate the value of the L lambda that satisfy the ratio of the dark energy at the present time. In other words, we can rewrite the parameter B in terms of the known number obtained from the observational data and L lambda. So we have only one parameter left, L lambda. By solving the numerically for the Friedman equation, you can see that in the past, corresponding to the much negative log A, the Hubble radius is much smaller than the non-intensive length scale. As time evolves, the Hubble radius get higher and higher. We have to evaluate that which value, the value of the L lambda that satisfy the approximation that I mentioned previously. So for L lambda equal to 0.1, can be treated as can be used the the large L limit that can drive the accelerated expansion. But in the past, the holographic dark energy from the Rényi behave like a scaling solution. Okay. By taking the limit, it is found that the Rényi holographic dark energy can recover the cosmological constant in the LambdaCDM. And another observational data from the Big Bang nucleosynthesis also constant that the L lambda should not too large. Just because if it's too large, it will be dominant in the parts over radiation or matter. So the structure like a planet, galaxies cannot be formed. So it is forbidden for the model. So the range of validity of the non-intensive length scale is lie on this from 0 to around 0.14. It is the result from the numerical calculation. We can see that the universe can be derived with the correct rate of expansion in the past, in the future, because the W goes to -1 in the future here. But if we take the low enough non-intrusive length scale, it smoothly reduced through the LambdaCDM here. So, move to the last part of the fitting, the non-intrusive length scale. We actually use the low redshift observational data. For example, if we consider the data from supernova, it is called the Pattern Plus dataset. Here it is the observable. It's called the distance modulus. You can see that from the definition of the distance modulus, it depends on the evolution of the universe that different for different value of the L lambda here. So the black line is the black dot and error bar here. It is the real data from the Plateau Plus. You can see that the data can be fit by the theoretical prediction from the Rényi holographic density model here. For example, if we consider like a quantity called chi-square, we can know which value of the lambda is preferred to fit the data from supernova. But in this work, I use the public code. It's called the simple MC to do the estimation, the cosmological estimation. It's actually the Markov chain Monte Carlo code here. You can see in this website for the detail of this code. By running this code, it turned out the value of is called AIC here, which is defined as here, where L is correlated infer the joy probability in observing data, and K here it is the number of the parameter, the model parameter. The key point is to determine the quality of fitting data. Which model has lower AIC? This means the model is better fitting data compared to others. So the last term 2K here is introduced to prevent the overfitting issue. And it is the scaling, the scale of the AC to interpret. If the difference between AIC is less than 2, is not different based on the statistic. But if it's lie on the range from 2 to 5, a bit different. The lower is a bit slightly better in fitting the data. If the AIC difference in AIC is greater than 5, it's much different, obviously different in fitting data. In this work, we put all the data set, which is from the cosmic chronometer and the BAO data, including the recent data, the 16. Here, it's just like put the run the code actually and find which value of lambda that give the AAC minimum. So this is the process that we evaluate the value of non-intensive length scale. It is found that it's around 0.07. It is just the result obtained from the simple MC. It is the distribution of the model parameter, not only for the dark energy. You can see here it is the matter all species including the dark energy. It is only baryon. Another parameter is the Hubble parameter at the present. Here it is the distribution over observational data set that we selected. But compared to different models, we have 4 models. The last two ones are the result from my previous work, that the holographic dark energy defining from the ADS black hole with standard Gibbs-Boltzmann entropy. But the key thing is you can see that the AAC for the holographic dark energy with fixing the non-intensive length scale looks slightly better than the LambdaCDM in fitting only the low redshift data. Here it is a summary of the result. It is possible to construct the cosmological model without the causality problem. And another remark, you can treat the non-intensive length scale as a characteristic length scale that compared to the size of the universe. In the past, the size of the universe is much smaller than the non-intensive length scale. So the behavior of the universe is expand with deceleration. But when the universe faces the length scale, the non-intensive length scale, it's become the accelerating universe. Another remark is if we investigate the perturbation, do the perturbation analysis for this kind of model, is impossible. It is because we have no field description, but as well as we cannot calculate the perturbation of the energy density and the pressure and the perturbation in the pressure independently, for example. So this cannot analyze the stability in this point of view for the holographic dark energy. This is all of my talk.
Okay. Thank you very much. It's very interesting talk. Even I'm not working in this kind of area, but I think there is something very interesting. Any question from the audience? Anything you? Okay.
So I would like to ask about the concept of the holographic dark energy. And
Yes.
in your talk, you present there are 2 ways to define the holographic dark energy. One that relates to, if I'm not mistaken, it's one that relates to the vacuum energy in quantum field theory, right? You have like the model like
It's actually defined like the the ordinary matter that has the maximum energy in which it doesn't form as a black hole. That's the key definition.
Okay.
Yeah, it's called also called the UVIR relationship. Yes.
Yeah. So so the formulation that you show in your slide is like your model, like in the vacuum energy in the box, right, with the UV cut off.
Yeah. It's actually the initial proposed
Yeah.
researcher.
That,
Yeah,
that
that
so
define.
my question is,
Mhm.
how the dark energy relate. I know that there are the model that relate the vacuum energy in quantum field theory. It can be interpreted as the dark energy, but observationally, there are problems in the order of magnitude. Like in quantum field theory, the order of magnitude is way far greater than the observable.
Mhm, mhm. Yes.
So is that the problem? I mean, maybe probably in your work or yeah. My question is the difference in quantum field theory and the observable one. That
Hmm.
yeah, is that be the problem here?
Oh, yeah. I understand the question, but I haven't considered in that aspect, like compute the vacuum energy from the specific quantum field theory, right? And evaluate the vacuum energy scale compared to the energy scale of the cosmological constant, something like that. Yeah. Mm, so I don't know. It's because in defined in different
Okay.
context. Yeah.
All right. Okay.
Yes.
Anyone else would like to ask? You can pick up. Would you like to contribute a question? Well, I have one myself. What you did is you start from ADS, right?
In the
ADS.
previous work, yes.
Yeah, and then you apply this model in the holographic dark energy, right? Is that right?
You mean this work or the
And
previous
the
one?
for the cosmology model here.
Oh, for today talk, I just consider the Schwarzschild black hole, not ADS black hole.
Okay. So okay. So what? Because my question is that our universe is not ADS, right? It's ADS, right? It's the ADS, not anti, right? Not yeah. That is
Not
something
entirely.
that confuse a little bit. Anyway, all right. I'm not sure that actually if you get something from that kind of perspective, you can use that kind of result to apply to 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 our universe directly. You know what I mean, right?
Interesting. You will get very interesting result actually.
Yeah. Anyway, okay. So
Probably
yeah,
more questions.
yeah. Okay, please, yes.
So related to the definition of the dark energy of the second one, the thermodynamic description of the dark energy that you
Yes.
at this is at like the rate of change of the mass of the black hole compared to
Yes.
the volume.
Yes.
Right? So uh, I would like to know the physics behind that. I mean, like, so is that mean the rate? So is that mean the rate of change of mass related to the the uh the dark energy density, right? So meaning that if you imagine like if the black hole grow up, so the mass got bigger and the volume get increasing, so that means the density got positive, so, right? So but in the case that if the universe or if the black hole is saturated, maybe the mass, there is no mass gets sucked into the black hole. So is that mean in that case there is no dark energy? Yeah, that's the question. So and I would like to know about the physics behind that definition as well. Why do they define the uh, density, dark energy density at the rate of the chain of the black hole as well?
It's actually not clear. We actually just define from the ratio of the mass over volume. It is still okay, right? It is what you mean?
No one knows actually.
Okay, so actually there are various ways to define. Actually, for example, like consider the derivative or just the ratio of mass over volume. But in this situation, I avoid the such a you mentioned situation from consider the situation that the black hole is just stable. So it is corresponding to the how to say there is no like a strain situation. It is because how to say the result of the derivative is well defined in the situation that make the how to say the non-intensive parameter constant under this change. So based on the thermodynamic stability of the black hole, the change will like this change will always positive, right? I try to avoid this too, actually. But the answer for the question that why we need the change, why we need to define the energy density from the change in mass compared to the volume, I don't know. It's still unclear for me.
Okay, if you okay, say okay.
As I
Okay.
check, if I check the possibility to interpret it as a dark energy, it's impossible.
Okay.
It
Thank you.
cannot drive the accelerated expansion. Actually, if I remember well, I try many approach actually.
Hello, Lad. I have
Crap.
some conceptual question. If okay, your energy is defined from the some cut-off scale, right?
Yes.
Energy density of your energy model depend on some cut-off scale, right? So if and
Yes.
the time evolution of the energy density of the energy depend on the time evolution of that cut-off scale. Is this correct?
Right.
Yes.
Right.
My question is that this is it implied that when your cut-off scale change in time, energy density of the energy change with the same rate everywhere in the universe. You mean when the cut-off scale change, energy density change, but in your formulation, energy density should change with the same rate everywhere in the universe. This is okay in your opinion? There are some problem. Is there some scale causality problem in this grade?
Oh,
Actually, I don't know.
I don't know too, but same with everywhere.
Because the energy depend only on the
Yeah.
cut-off scale. Yes.
You mean in his model, right?
Yes, yes.
Oh,
If you don't know, say don't know.
I don't know. To be honest, I don't know.
We can move on then. Okay, well, I think you can discuss with Ajahn Kampi later about this point. Right, okay. I think it's about time, and I would like to thank Lad again for this very interesting talk. And so before everyone leave or we go, please complete the survey form for us, and stay tuned for the next colloquium, probably next year, because next one we are not going to have colloquium talk. For next month, we're going to start a new one in January. All right. Okay. Thank you very much, everyone. Bye bye.
ขอบคุณครับ บ๊ายบายครับ